Welcome to this session number 6. Again, we will continue with the torsion concepts, which is there in the model number 4 of the syllabus. So here, until now we discussed about the straight shafts and we solved some problems on the straight shafts with constant diameter. So in particular applications, we have shafts like this, which are called as stepped shafts. So here the diameters of the shafts will be different for different lengths. That's the one thing. One more thing is that the torque applied will be at different points on the shafts depending on the applications. So here we have some problems where the condition is statically indeterminate. So we don't only equilibrium equations will not satisfy or not enough to solve the problem. We may have to use some compatibility equations also for statically indeterminate problems. So in this session we look at stepped shafts and where the torques are applied, different torques are applied at different cross sections of the shafts, and we will try to design the shafts for this kind of applications. So here in this slide I am using the units with FPS units. So in the previous case we used MKS and SI units. So don't worry about the units here. Just understand the concepts with respect to the problem here. So here we have a shaft, particularly a stepped shaft, with which is made up of different material. So you can see one portion of the shaft is made up of aluminium, other portion of the shaft is made up of steel, and the diameter of this portion is different, and diameter of this portion is different. So this is called as a stepped shaft. And one more thing is that the two ends are fixed here. The two ends are fixed relatively, and a torque is applied T. Anti-clockwise torque is applied T. So in this case, since the two ends are fixed, the torque is applied at the two ends, reactional torsional torque will be developed here. So for equilibrium conditions, the torque, whatever is applied, external torque, is balanced by these two reactional torques here, which are opposite in nature. If this is anti-clockwise direction, the reactional torque will be in the clockwise direction. So this is the torque developed by the steel portion of the shaft here, and this is again the shaft or the torque developed because of this sectional torque to maintain the equilibrium in the aluminium part of the steel of the shaft here. So here what happens is that for equilibrium condition, sum of all the torque should be same. So here you can see this is clockwise. If you take this as anti-clockwise as positive torque, the clockwise torque will be negative. So if you add all the things for equilibrium condition, the sum of all the torques or moment will be 0. And since it is a statically indeterminate problem, only this equation is not enough to solve the problem here. And coming to the problem here, we have to find out the maximum stress developed in each portion of the shaft here when torque is applied. So this portion is made up of different material, this portion is made up of different material. So obviously the shear stresses developed in these two materials will be different. So only with this equilibrium condition we cannot solve the problem. So thus it becomes a statically indeterminate problem. So apart from this equilibrium equation, we have to make use of compatibility equation here. So compatibility equation here is that the angle of twist at B, at this portion, at this cross section where the material changes, or at the step here, the angle of twist will be same in both the portions here at this point here. So since the torque is applied here, the shaft twists with the same amount on both the portions. That's why if you take the angle of twist for aluminium and angle of twist for steel, it should be same at this portion here. So that is the condition of our compatibility. So the two portions should have the same angle of twist. So the angle of twist for steel portion will be same as, will be equal to the aluminium portion. So here we'll take the torsion equation with respect to angle of theta. So T by J is equal to G theta by L, so that it is taken in terms of theta now. So theta steel, angle of twist for steel will be TL by GJ for steel. Similarly, angle of twist for aluminium will be TL by GJ aluminium. So here G, rigidity modulus of, since the materials of the shaft is different at different portions, the rigidity modulus of aluminium will be different and rigidity modulus of steel will be different. We cannot take it as same. So it is steel, G steel is different, G aluminium is different. And J, since the shafts are of different diameters, J also you have to calculate separately with respect to the diameters. And torque of the steel and torque of the aluminium at the aluminium portion will be different because the material is different. So torque induced or torque developed, reactional torque developed will be different for steel and different for aluminium. That we have to find out. And length, anyway, the length of the steel portion is given, length of the aluminium portion is given. So it is, length is not same for both the portions here. So this is for aluminium portion of the shaft, length is 6 feet, and for steel portion it is different. So you cannot take same lengths in this problem here, just like unlike other previous problems what is solved. So looking at these conditions and taking different given values for all the parameters in this equation, so here we can see that the torque in the steel shaft is different when compared with the torque at the aluminum portion of the shaft. So when all the values are substituted here, this G is given and G for aluminum is given, substitute that. J for the solid, it is solid shaft here, so pi by 32 d to the power of 4. So the diameters are given, if I substitute that, you will get the relationship here. So the torque of the steel will be 1.18 times of the torque in the aluminium portion of the shaft here. So here this is the one equation, that is equation number 2 or B, and we have, this is a compatibility condition, and in the previous case we have the equilibrium condition that the sum of all the torques should be equal to 0. So substituting this now, so T steel, if you substitute this torque in steel as aluminium, we will get the torque in aluminium as a Newton meter or pound inch. So this is a different system, don't worry about that. So it will be, torque will be Newton meters or Newton millimeters. So once you know the torque in aluminium now, using this equation you can get the torque in steel also. So here you can see that aluminium portion develops 4000 around 4,500 Newton meter, and steel develops 5,500 Newton millimeter. So in this problem the steel will develop 5,500 Newton millimeter torque. So this torque is 5,500 Newton meter, and the torque in the aluminium, this reaction torque will be 4,500. So if we add these two, it will be equal to this one. So 4.5 plus 5.5 will be equal to 10. So if you apply 10 Newton meter at the portion here, so at this steel part it will be taking 4.5 Newton, and the aluminium will develop 5.5 Newton meter of the torque here. So this applied torque will be shared by these two torques, these two portions of the material. So since the torques are different in different portions, the stresses also will be developed differently in aluminium and steel. So directly we can make use of the torque equation, that is T by J is equal to tau by R, and you can calculate the tau or tau max for aluminum and for steel. So since all the diameters and torque is known, it is easy for us to calculate the shear stresses developed in aluminum and steel. So you can see that aluminum developed shear stress will be 863 and shear stress in the steel will be more, 3450 Newton per meter square or whatever it is. So since aluminum is having torque in the aluminum is less, shear stress developed will be less because both are proportional here, and the torque developed in the steel is more, so the shear stress developed also will be more. So as the torque increases, the torque developed induced in the shaft will give rise to more and more shear force, and shear stresses will be developed here. And also steel diameter is less compared with the aluminum, so obviously the shear stress in the steel will be more because D is in denominator here. So you can see that shear stresses, it will depend upon torque and the cross-sectional area of that material. So we have one more problem here where the shaft is straight, but the torque applied will be different at different points on the shaft. So this is the example of gears. You just imagine that these are the gears which are rigidly fixed on the shafts, and when they are operating, the gears are in contact with the relative gears, corresponding gears, and due to the rotation, torque will be applied on these gears with different magnitude. So here you have 4 gears A, B, C, D, and the length of the shafts will be different. The position of the gear will be different on this shaft here, with a difference of 4 feet, 3 feet, 5 feet. So these are the length of the shaft for calculating, and on this shaft we have the different torques at different points here. So at point A we have 500 Newton meter, 900 Newton meter clockwise, 1000 Newton meter anti-clockwise, 600 Newton meter clockwise here. So like that we have to analyze the torques, and we have to find out the angle of rotation, that is the angle of twist of gear A relative to gear D. So you can see here torque applied here, here and here. So the angle of twist will be different here, and the angle of twist will be different at this portion. So it's asking you to calculate the angle of twist with respect to angle of twist here, and the rigidity modulus of the shaft is given, and diameter of the shaft is given. So only these two data is given. Diameter is given, length is given, and the rigidity modulus of the shaft is given. We have to calculate the angle of twist here. So here, since the different torques are given at these points, so angle of twist for this portion will be different, angle of twist for this portion will be different, so angle of twist for this portion will be different. So this full shaft we will try to separate them individually with the different portions here. So A and B, we have one portion of the shaft AB, B and C is one portion, second shaft, and C and D is third shaft. So the torque or the angle of twist for portion AB we have to calculate, the angle of twist for BC we have to calculate, the angle of twist for CD we have to calculate. So if we add angle of twists for 1, 2, 3 shafts, that will be the angle of twist at D. So here we will try to simplify this problem with free body diagram here for different portions of the shaft here. So here he is taking vectors with right hand tool. We are representing the torque as vectors here, or else we can directly go to the right hand rule here, and we calculate, we draw the free body diagram here. So instead of taking vectors here, we'll take the torque only directly. So one simple simple solution is that we take the right hand side of the shaft here, and here we'll try to understand what are the torques on the right hand side of the shaft. So this, since it is the dead end of the shaft here, the only torque applicable is 500 Newton meter. So if you take this portion of the shaft AB, the torque applied will be 500 Newton meter in the anti-clockwise direction. So for portion AB, the torque is 500 Newton meter. Now come to this cross section, that is point B. So at point B, you consider the torques on the right hand side of the point B. So on the right hand side of the point B, we have two torques with 900 and 500, and 900 is clockwise, 500 is anti-clockwise. So if we add that, we'll get 400 Newton meter with clockwise direction. So the for BC, portion BC, at B, the torque is 400 Newton meter. You can see here it is, for torque at portion BC is minus 400, since it is clockwise, and the torque at AB is 500 anti-clockwise direction. So anti-clockwise direction is taken as positive. So for portion AB, the torque applied is 500 Newton meter anti-clockwise direction. And for portion BC, you take the right hand side, you calculate the torques here. So it is 900 minus 500. So it is 400 Newton meter, and it is clockwise. So clockwise is taken as negative. So the torque on the BC portion of the shaft is minus 400 Newton meter. And coming to portion CD, you take the point C now. You take point C and you add all the torques on the right hand side of the C. So on the C it is 1000 anti-clockwise, then here it is 900 clockwise, so 1000 minus 900 is 100 anti-clockwise. Then here we have 500 anti-clockwise, so 100 plus 500 will give you 600 in the anti-clockwise. So for portion CD, it will be 600 Newton meter anti-clockwise direction at C, and it will be equated, balanced by clockwise direction torque 600 Newton meter. So for portion CD, the torque is anti-clockwise 600 Newton meter. So this is how you have to analyze the torques at different portions of the shaft. So just to take the portion AB first, and at A the torque is 500 Newton meter. So for portion AB, the torque will be 500 Newton meter anti-clockwise. And come to point B now. So point B, on the left hand side you take portion BC. So this is portion AB, next portion is BC. So on the right hand side you take the point B and you just add all the torques on the right hand side of the B. So at B it is 900 clockwise, and at A it is 500 anti-clockwise. So 900 minus 500, so you will get minus 400 here. Minus means it is clockwise. So the portion BC, the torque is anti-clockwise 400 Newton meter. And coming to this portion CD, you take the point C here. So at this point you just add all the forces, all the torques on the right hand side of this C. So at C it is 1000, in this direction, at P it is 900 in the other direction, so difference will be 100 here, and one more torque is here, 500 in the anti direction, so it is 100 plus 500 is 600. So that is balanced by this torque at D. So a portion CD we have 600 Newton meter torque. So once we analyze the torques, we can say that the summation of our torques will be same for equilibrium conditions. So for anti-clockwise direction torque we take positive, for clockwise torques we will take it as negative. So this is the convention what we are using for torques. So the compatibility equation here is that I told you before that angle of twist at A and D at D is equal to sum of angle of twist of portion AB, portion BC, and angle of twist for portion CD. If we add all the angle of twists, all the shafts, the angle of twist at the point D, it is the summation of all these angle of twists. So since we know the angle of twist theta with respect to, we can use the torsion equation again. So T by J is equal to G theta by L. So since the value of G is given, we can calculate the angle of twist and we can compare that. So here you can see that angle of twist of AB is TL by GJ, and angle of twist portion BC is TL by GJ. The equation is same, but we will be taking different portions. Length of AB is different, length of BC is different, length of CD is different, and the torque AB is different, torque BC is different, torque CD is different, and TL by GJ. So since the material is same, G will be same for all the portions of the material of the shaft, and J also will be same because the diameter of the shaft is same. So this is common here, G and J. So if you add all the angle of twists, you will get the angle of twist at the point D with respect to relative to A. So here torque at AB, torque in the portion AB we have just calculated, it is 500 Newton meter. Torque in BC we have calculated it as negative 400 Newton meter. Torque in CD is 600 Newton meter, and lengths are given for different portions, it is different. So for AB it is different here, for BC it is different, and for CD it is different, 4 feet, 3 feet and 5 feet, or you can take it in meters if you want. And G is given, it's a material property, rigidity modulus is given, you can directly substitute that value, and J is nothing but pi d to the power 4 by 32. The diameter of the shaft is same. If it is different, then it will, if for example if diameter of portion AB is different, then it will become JAB. Then if the diameter of BC is different, it will become JBC. J will be different for BC, and if diameter of CD is different, then J value will be different for this CD. So then only G will be constant here, which is you can take it outside. Only G will be same, you can take it outside, and we'll put TL by J, TL by J, and TL by J. Since it is diameter same, J will be same here. So just simplify that, substitute the values, and you can calculate the theta. We'll get in radians. So if you multiply it by 180 by pi, we'll get in degrees, because pi radians is equal to 180 degree. So if you multiply it by 180 by pi, you will get I think 1.62 degrees. So since it is positive here, So the shaft is rotating in the positive x direction, and it is anti-clockwise. Theta AD is directed anti-clockwise, so it is the shaft is rotating in the anti-clockwise direction when you see from A side. So here the shaft is rotating with the resultant of these torques. The shaft is rotating in the anti-clockwise direction when you see from this side. So the torque angle of twist will be 1.2 degrees here at this point, 1.6. So this is one example where we will be using compatibility equation as well as equilibrium equations to calculate the shaft angle of twist. So in the first problem, the angle of twist was same. In this problem, angle of twist was same, but torque was different. In this problem, torques are different for different portions, as well as angle of twist is different. So the angle of twist at the end will be summation of all the portions. So we have some more problems where we have a stepped shaft with one end fixed and the torque is applied at the other end. So here this is the shear stress of this metal is we have two materials. It's a stepped shaft with the two different materials. One is made up of brass alloy and other one is made up of steel alloy here. So the shear stress of the brass is given 80 megapascal. The shear stress of steel is given 100 megapascal. You have to calculate the maximum torque that can be applied here. The T you have to calculate, so how much you can apply, so that the ends, that is and also you have to calculate the total rotation angle of twist of this end with respect to the fixed end, and this modulus is given here. Rigidity modulus for brass and steel is given, and the shear stress is given for these two materials. So rigidity modulus and the shear stress is less for brass than steel here by numbers. So this is the applied torque. So this torque at this portion will develop a reactional torque which is opposite to this torque, and this portion will develop reactional torque, and the same torque will be applied here on this portion, and at the fixed end reactional torque will be developed here to maintain the equilibrium. So this is the free body diagram of the torque applied. So whatever torque is applied at T at this end, it will be transferred at this end A. It will be opposite in nature. So this is T at C, at this end C, torque is clockwise. So to maintain the equilibrium, reactional torque will be developed at A, which is in the opposite direction. So this is clockwise T. So here whatever torque is applied, it will be same for both the portions here. So here you can see that both the portions are subjected to same torque T, and here we have a different step. Since it is a stepped bar which is made up of brass and steel. So if you take AB as the first portion made up of brass, BC as the second portion. So first we will take the brass rod, that is portion AB. So T by J is equal to G theta by L. Or you can take it as shear stress by radius. T by J is equal to tau by R. So the shear stress of brass is given here 18 Newton per meter square. The diameter of the brass is 80 millimeter. So radius will be 40 millimeter. So T by J is equal to tau by R. So since it is shear stress is given, we take the shear strength equation. T by J is equal to tau by R. So directly tau is given, radius is given for the brass rod shaft here, and diameters are given here. Torque we can find out easily here. So similarly, you can find the torque of the steel bar here. So in steel bar again, you can see that torque developed will be again T by J is equal to tau by R. Tau is 100 megapascal, R is 30 mm, diameter is 60 mm for the steel rod. So we can see that the torque developed here is 42,41150 Newton millimeter, and this is 80,42,477 Newton millimeter. So here the maximum torque that can be applied is, this is maximum here. So here you can find out the angle of twist at the free end. So it is nothing but summation of the two portions of the bar here. So if you calculate the angle of twist with respect to the brass shaft of the portion and steel portion here, and you are taking the maximum torque as 424 or 4200 kilonewton millimeter here. So that comes to T is, that's the maximum torque that can be applied, and you can calculate the angle of twist here. So you will get it as 0.076 radians. You can convert that into degrees. So here the angle of twist of at C with respect to A is summation of these two twists here. So we have one more problem here. So here it is again a stepped shaft, and you can see it's a combination of two solid shaft and one hollow shaft with the different diameters and length. So just look at the data here, all the data and the diagrams here, and we will calculate the angle of twist at this end. So what is the angle of twist we will be getting here? So that angle of twist will be equation is nothing but again sum of all these portions here, and since the material is same, the value of G is given, and it is a material is same, all the portions of the bar are same material, so G is common here. So here, so this, for this configuration you will first put the free body diagrams and find out the torques in each portion. So since different torques are applied at different points on the shaft, we have to analyze the torques on each portion separately. So with respect to free body diagram here, so first we'll take the right hand side portion, that is CD. So this is CD, and on this CD we'll take the right hand side torque at D. So at D the torque is 1 kilonewton meter anticlockwise. So you can see at D it is 1 kilonewton meter anticlockwise. So the portion, the other end of the portion bar is CD is point C. So at D, if it is 1 kilonewton anticlockwise, at C it will be clockwise 1 kilonewton, equal and opposite. It will be same. And coming to portion BC now. So you take the point, now consider the point C, and you add all the torques on the right hand side of the C. So at C it is 2 kilonewton clockwise, at D it is 1 kilonewton anticlockwise. So 2 minus 1. So 2 is clockwise, 1 is anticlockwise. So 2 minus 1, you have to add, you will get 2 minus 1 as 1 kilonewton meter clockwise. Since these two are opposite, we have to minus it, we have to subtract 2 minus 1, and since it is 2 is greater than 1, the torque will be clockwise. So in portion BC at C, the resultant torque will be 1 kilonewton meter clockwise. And in portion BC at C, if it is 1 kilonewton, at B it will be same and opposite, equal and opposite. So if it is clockwise here, it will be anti-clockwise at 1 kilonewton meter. So at portion BC, the torque exerted is 1 kilonewton meter, and on CD also it is 1 kilonewton meter. Coming to portion AB, you take the point right hand side of the portion B, and you add all the torques on the right hand side of the B. So at B it is 3 anti-clockwise. So 2 at C it is 2 clockwise. So 3 minus 2 is 1, which is anti-clockwise, and again it is anti-clockwise 1 is here. So 3 minus 2 plus 1. So 3 minus 2 is 1, 1 plus 1 is 2. So we get at P the total torque is 2 kilonewton meter anticlockwise. So in portion AB at B, if it is 2 kilonewton meter anticlockwise, at A it will be equal and opposite. So we will get 2 kilonewton meter in the clockwise direction. So this is the free body diagrams of the different portions of the shaft here. You can see here. So now we treat this shaft as different, and each portion of the shaft is experiencing different torques here. So now we can calculate the torque. Torque is known for each portion. We can calculate the theta for each portion, and if we add that, that will be the angle of twist of the shaft. So now, since the diameters are different, J value will be different. So for portion AB, polar moment of inertia J will be since this is the hollow shaft, we'll get pi by 32 outer diameter minus inner diameter. So we'll get this value. Similarly, portion BC is solid, so polar moment of inertia will be different. We calculate this. Similarly, CD is a solid shaft. We put the same formula and calculate this. And we want to calculate the angle of twist. So it is torque. So torque in each portion, length of each portion, and the solid shaft is made up of same material, all the portions. So G is common. J, it is, since it is a stepped shaft, it will be different for different portions here. So to calculate the total twist, so we have to add all the angle of twist at AB, angle of twist at BC, angle of twist at CD. So here you can see that we are taking anti-clockwise as positive. So angle of twist will be positive here, negative here, and positive here. So angle of twist will be positive here, AB, BC it will be negative, and CD it will be positive. So angle of twist at AB minus angle of twist at BC plus angle of twist at CD. If you take the summation, you will get the angle of twist at the free end, or the total angle of twist of the shaft. So using this equation, so take G common or separately and substitute the values. Torque we have calculated for each portion, length is given, so it is different for different portions, and J we have calculated it for different portions. So just use this equation, add individually, and if you substitute that, we will get this in radians. So once the angle of twist is found out, and once we know the torques in the different portions, we can also calculate the shear stresses in each portions of the shaft. So if you want the shear stress to be calculated, we can make use of the torsion equation for shear stress. So T by J is equal to tau by R. So QS is nothing but tau here, shear stress. So T by J is equal to tau by R. So in first portion, since the torque is known for portion AB, torque you have to substitute here, and J value you have found out now. R is known, so you can easily calculate the shear stress tau in portion AB. So shear stress is equal to T into R by J. So this is the torque, this radius, this is J. Similarly, the same equation holds good for second portion BC. So tau shear stress for BC is again T into R by J. So we know all the values, we substitute and get the portions, shear stresses in all the portions. So you can see that shear stress in AB is 17 megapascal, BC it is 9, and in CD is 23. So this problem we had solved earlier. So it is where the two ends are fixed, and here some torque is applied at some distance. So the total length of the shaft is 600 plus 400. At 600 millimeter length, we are applying 2 kN/meter, and here this part of the portion is shaft is hollow. This part of the portion is solid shaft, and the material is same, I think. So the material is same, but here it is hollow shaft. A hole is drilled inside the shaft here to make it hollow. So for 400 meter it is hollow shaft, for 600 millimeters it is a solid shaft here. Material is same, the G will be same, rigidity modulus will be same, and outer diameter and inner diameter is given, and length is given, and torque applied is given. So since the torque is applied here at different points, so we get different torques in these two shafts here, because the metal since the metal is same but it is hollow and solid shaft, torque developed will be different. So here one compatibility equation is that the torque will be shared by these two portions. So torque applied T will be equal to torque in portion AB and BC. So that you can see here, T1 be the torque in portion AB and T2 be the torque developed in BC. So you can see that the torque what we apply will be summation of the torque developed at these two portions. So here we'll take the angle of twist. So here angle of twist will be same. So in case of compatibility equation, angle of twist will be same for both the portions. So since so we calculate the angle of twist for both the portions, and will be leaving T1 as it is, and we will get the angle of twist with respect to T1 and G. The G is the material property, rigidity modulus is not given, but we'll keep it constant. We'll see it later. And similarly for portion BC, the same formula holds good, and we'll get the theta 2 with respect to T2 and G. So since theta 1 is equal to theta 2, we will get these two equations now. When you get these two equations, G will get cancelled out because it is constant for the material, and we get the relationship between T1 and T2. So T1 is 0.7 times of T2, and since the applied torque is shared by both the portions, T will be equal to T1 plus T2. So we will substitute this here, and we will get the value of T2. So once T2 is known, we can calculate T1 also. So if we add these two, we will get 2 kN applied torque. So once the torques are found out, we can calculate the shear stress by using this torsion equation for both the portions. That's it for this session. Thank you.